topic left to talk about in this chapter before we can wrap things up. So up until this point, we've been worried about taking a polynomial, getting it into factored form, and then using those factors to solve, right? So here we want to kind of do the reverse. We want to take some information about the polynomial and build out and create a polynomial that kind of fits some criteria. So what we're doing today is we're going to talk about how to find a polynomial that fits some criteria. And we're just going to do this kind of by example. So let's say we want to write down a polynomial where all the factors have integer coefficients. It has the solutions 1, 1, 2, the square root of 3, and negative 2i. And the polynomial has minimum degree. So if we want all of our factors to have integer coefficients, what this means is that we have to make sure that the irrational conjugates theorem and complex conjugate theorem are followed. So if we recall what the irrational conjugates theorem says, is that a polynomial with integer coefficients has a irrational solution if and only if those irrational solutions occur in conjugate pairs. So if I look at my list of irrational solution, or my list of solutions here, are any of these irrational? So the square root of 3 is irrational, right? So if I want to have integer coefficients, I need to add another solution to this list. It needs to be the conjugate of the square root of 3. So what is the conjugate for the square root of 3? Negative square root of 3. Then we have to check the complex conjugates theorem. The complex conjugates theorem says something very similar. If you have a polynomial with integer coefficients, has an imaginary solution if and only if the imaginary solutions come in conjugate pairs. So if I look at my list, do we have any imaginary solutions on our list? Negative 2i. So I need to make sure its conjugate has also appeared on the list somewhere. What is the conjugate to 2i? Or I'm sorry, negative 2i? Is positive 2i. Is everybody okay with that idea? So we're done with this thing now. Everybody's okay there? Okay. Now we're going to move on to this criteria. So what I'm going to do is I'm going to write down each of these solutions separately. And notice I wrote the conjugate pairs next to each other just for convenience. Now, what I'm going to do to each one of these equations, these are equations, right? They have an equal sign in them, is get them equal to 0. So for x equals 1, I'm just going to subtract 1 from both sides. For x equals 2, I'm going to subtract 2 from both sides. For x equals the square root of 3, I'm going to subtract the square root of 3 from both sides. And I'm going to add the square root of 3 to both sides. I'm going to add 2i to both sides. And then I'm going to subtract 2i from both sides. Everybody okay with that idea? So now I have, instead of having, what do I have, 7 equations that were all equal to something different, I have 7 equations that are all equal to 0. Does everybody see that? Okay. What I'm going to do now is I'm going to multiply all of these equations together. So that means I'm going to multiply the left-hand sides all together, and then multiply the right-hand sides all together. Everybody okay there? Now what I have here is I have a factored polynomial that expressly has those solutions, right? Because when I set this thing back, each of these back equal to 0 and solve, I get exactly those solutions. Is everybody good so far? I have one more thing to take care of, and it's back here. It says all the factors have integer coefficients. If I look down here, I have some factors that do not have integer coefficients, right? Because I have square roots of 3 and then 2 i's. Everybody see that? So right now, this is not quite finished. To finish this, all I need to do is to multiply these pairs together. So when I multiply this out, I'm going to FOIL. And similarly over here, I'm going to FOIL. Everybody good with the foiling that I did there? Look at what happens, though, when I combine my like terms now after I foil. I have an x square root of 3 and a minus an x square root of 3. What does that do? Those are going to cancel out, right? Similarly, if I look at the next factor, I have a minus 2ix plus 2ix. What happens there? Those cancel out. Okay. Now, if I look at that factor, I have a square root of 3 squared. What is the square root of 3 squared? Just 3, right? The square root of 3 squared is the square root of 9. And the square root of 9 is just 3. Or you can think about the squared canceling the square root. Okay. Now let's look at that minus 4i squared. What does I squared equal again? I squared is negative 1. So negative 4 times negative 1 is 4. So there is my factored, or there's a polynomial whose factors all have integer coefficients. If I set this equal to 0, I'm going to get exactly the zeros that I listed. And when I wrote that third criteria that it has the minimum degree, what do I mean there? I mean it has the minimum degree so that it meets all the other criteria above it. Basically what that means is I didn't include like an extra stick on like an x plus 7 at the end for no good reason, right? That's all that the minimum degree part is saying. So as long as you don't do anything extra, that part will be satisfied. And that's it. That's basically, they all kind of work like that. Let's look at a couple more examples though, just to make sure that we got the hang of it. Yeah, of course. So let's say we want this time the factors have integer coefficients. Our solutions are -1/2, 3, 3, and then 2 minus 5i. I want minimum degree. And let's say a leading coefficient of 6. Yes, Caden. No, right? Like these are still the same 3 here. I've just added one more. Okay. So again, we're just doing some more examples. The criteria are basically going to look the same. There's only so many things I can ask you to do. No, that would be a perfectly reasonable example of something I'd ask you to do. Again, we have all the conceptual things that we need to do these problems. It's just doing some examples of, it's a different process. I'm asking for a different thing, but I'm still kind of using all the tools that we've already built out. So there's not much that we need to develop to do this. It's just kind of doing some examples. Yeah, no problem. All right. So first thing we got to do is make sure that our list of solutions meets the irrational conjugates theorem and the complex conjugates theorem. So if I look at my list of solutions, are there any irrational numbers on this list? Irrational. Are there any irrational numbers on this list? No, right? All of those, there's no square roots anywhere on there, right? Okay, so we don't have to do anything for that part. Next, let's look at the complex conjugates theorem. So look at my list of solutions. Are there any imaginary things on our list? Yes. So this is imaginary, 2 minus 5i. So what other solution needs to appear on our list then? It has to be the conjugate, which would be what? It's 2 plus 5i. So remember, the conjugates, the only part that changes is the sign on the imaginary or the irrational part. So either way. Everybody okay there? All right. So just like we did before, I'm going to convert each one of these into a factor. What factor does x equals negative a half turn into? X plus a half. What factor does x equals 3 turn into? It's minus 3. I'm just, right now all I'm doing is kind of skipping some work, right? Everybody's okay with that? Okay. And then we have another x equals 3, so I'll have another x minus 3. Now this step I'm going to write out a little bit just so it's easier to see what it is that I'm going to do here. So I have x equals 2 minus 5i. I'm going to treat 2 minus 5i as one thing. So I'm going to subtract 2 minus 5i from both sides, like that. And you're going to see in a moment why I'm going to do that, or why that's helpful. But it just makes things a little bit easier to deal with later on if I do it that way. Everybody, so far so good? Okay. Now we need to go back and we look at these factors and make sure that we have integer coefficients. Well, just like before, these don't have integer coefficients. So I'm going to multiply these two conjugate pieces together. But there's another factor that doesn't have integer coefficients. Which one is that? X plus a half, right? A half is a fraction, that's not an integer. So what can I do to x equals 1/2 so that it has whole numbers in it instead of fractions? What did you say? Okay, so that's still not going to be a whole number in it though, right? Even if I call a half 0.5. So that's not going to quite do it. Can I just multiply it by something? Yeah, what if I just multiply that factor by 2? That'll get rid of the fraction, right? Could I multiply by some number other than 2 and still do it? Yeah, right? Any even number will work, right? So go look at that fourth criteria there. The fourth criteria says we want a leading coefficient of 6. If I look at this right now, what will my leading coefficient be? It'll be 1, right? Because eventually, to get the leading coefficient, it's just going to be when I multiply all of these x's together, right? I need my leading coefficient to be 6. So let's put a 6 out front. But I'm not going to write it as a 6. I'm going to write it as 2 times 3. Why would I write it as 2 times 3? Because the 2 I'm going to multiply into this one to get rid of the fraction inside of that one. We did a lot right there. Is everybody okay with what we did and why we did things? Okay. So let's do our multiplication then. So 3, I'm just going to leave that there. When I multiply the 2 through, though, x plus a half turns into 2x plus 1. I can rewrite those next two just as x minus 3 with the squared on it. And this piece I need to FOIL. Yes, sir. Uh-huh. Is everybody okay here on how I FOILed that out? So now, before I can combine like terms, I'm going to need to distribute these things through. And I'm going to have to FOIL those pieces. Okay, so I have x squared minus 2x minus 5i minus 2x plus 5i plus 4 minus 10i plus 10i minus 25i. So that's gotten really ugly, but it's about to get pretty nice. If we go to combine our like terms, notice that, I have a minus 5ix and a plus 5ix. Those cancel out. I have a minus 10i and a plus 10i. Those cancel out. And we remember that I squared is equal to negative 1. So I have an x squared minus 4x, and then I have a 4 minus 25 times negative 1, which would be positive 25. And now I have all my factors have integer coefficients. If I multiplied out, my leading coefficient would be 6. And if I set this thing equal to 0 and solve, I'm going to get exactly the solutions that were listed above, right? So we're done. Is that one okay? Let's do one more example, and then we'll call this a day. Does that sound okay to you guys? All right. So here my criteria are, again, we want factors with integer coefficients. We want the solutions minimum degree, and then let's say no constant term. Well, we know how to cover these first three, right? We've done those all, situations like those ones all before. So let's just start there. We'll worry about the no constant term at the end, maybe. So, again, we start here. I want to worry about the irrational complements theorem, or conjugates theorem, and then the complex conjugates theorem. If I notice, there's only one factor, or one solution there that's an issue. 1 plus I square root 3. So what other factor, or whatever, I'm sorry, what other solution needs to appear on my list? So it's 1 minus I square root 3. So again, the only thing that changes is the sign in front of the imaginary or the irrational part. Okay, so only one sign is going to change. So if I write my factors, then I should have that, right? Everybody okay with how I created those factors? I notice that these two factors don't have integer coefficients, but the conjugate pairs, we can fix that just by multiplying them together, so I just need to FOIL that part out. Okay, and just like before, I'm going to distribute here and then FOIL there. So that's a plus. And if I go and I look to combine my like terms, I have a plus I square root 3x and a minus I square root 3x. So those cancel. I have a minus I root 3 and a plus I root 3. Those will cancel. My squared cancels my square root, so I'm left with just 3. And we know that I squared is negative 1. So I'm going to have x squared minus x is minus 2x. Then I have 1 minus 3 times negative 1, so that would be plus 3. Oh, I'm sorry. 1 plus 3 is 4. Ay, ay, ay. Okay. Now we still have one piece of criterion left to worry about, right? We only covered the first 3 there and what we did. If we go back up, we still need to worry about no constant term. So right now, what is the constant term going to be when I multiply this thing out? Well, eventually I'm going to have to multiply these things together, right? So my constant term would be 24. Everybody agree with that? A polynomial with no constant term, what would the last term be then, if it has no constant term? It'd have to end in with like something x, right? Like 1x or 10x or 15x or whatever. But that would be the last term in my polynomial if there's no constant term. Does everybody agree with that? So what can I do to this to get rid of that constant term? Right now, this ends with whatever, and then it's like plus 24. I need it to end with whatever times something x, right? So what can I do to the polynomial we have so that we end with something x? Let's just hear some ideas. It's not entirely clear how you would do this, probably, right from the jump. So let's talk about it. It's not a difficult fix, but it's a sneaky fix. What if I just say subtract 24 at the end? Will that work? Is that the fix that I need? It would definitely take care of the no constant term part, but it would end up ruining all of these solutions. So I can't just subtract 24 from both sides. That's not going to cut it. So if I can't add or subtract something, what else might I be able to do? Multiply by something. Okay. What could I multiply this by so that the last thing would have an x on it? So we're going to multiply this by something so that I have the last term then ends with an x. Oh, so close, guys. Right now it's 24, and I want it to end with x, or something x. The x can have a coefficient on it, that's fine. But it has to have an x with it, whatever it is. 5x, 10x, 15x, whatever. X. Yes, that'd do it. So if I multiply this by x, I'd end up with something plus 24x, right? Everybody agree? And that'll do it, right? Is that going to affect the solutions? No, because I still have this thing equal to 0. So when I set everything equal to 0 and solve, there's no problem. If I had the minus 24 there, I'd have to add the 24 over, and then I can't set everything equal to 0 anymore because it's not equal to 0. But that'll do it. So just tacking another x on out front is all we needed to do. It was an easy fix, but it probably wasn't obvious that that's what you would do to kind of get rid of that constant term, right? We had to think about that a little bit to get there. Okay. Madison. Sure. So this wraps up chapter 6 for us. This was the last thing we need to talk about.